used to be solid, not falling apart. Things never not okay when you were mine. You used to be honest, not pulling my heartstrings. Every other day you change your mind, 'cause when you're high.
Hello everybody and welcome back to this next part in this livestream series. Up until now we have finished the original implementation of the LDSO, which you can see here at the moment. And now it is time to experiment, to bring in own ideas and to see what we can find out about the internal working of the LDSO. So the plan for today is to firstly fix a bug, because I noticed that during the initial write down of the code base, I have actually made a mistake, which we can see in a minute when we change the dataset. Because currently we are using the sequence 45 from the TUM monocular benchmark dataset, and this is working fine. But if we switch to, for example, sequence number 2, we will see that there will be basically an exception, an assertion which will fail, and this is due to a mistake that I made. So I will need to fix that. So this will be the first task that we will tackle together. Then the next part will be to look into the code base a little bit more by debugging. So currently we have a debug build running here, and that means we can look into the individual parts of the code to see how certain things are working. I think we will keep it quite superficial today, so we will just look at what kind of function calls are being made in sequence and try to get a rough overview of what parts are involved to process one image of our image sequence. So this will be the second task, and the third task we will tackle today is we'll try to change something about the LDSO implementation. I actually thought more about visualizing the trajectory and the point cloud within Blender. This is not really related to the LDSO, but maybe we can somehow connect those things. So actually, as a third task, I thought about taking the result that is generated here and putting this result into Blender so that we can visualize this outside of the LDSO. And this will enable us to, for example, evaluate the performance of the algorithm, or try to use the data in different environments so that we can, for example, do some maybe not augmented reality, but combining the real data, so processing the video sequence within this LDSO here, and then loading up this information in Blender, for example, to integrate other 3D objects into that. Those are just very basic applications of having this LDSO algorithm running, but it will help us to understand what is going on behind the scenes. So by taking a look at the point cloud data, looking at the trajectory performance, we can see, maybe we can find out problems. And ideally, what I would like to do is I would like to generate my own data sequence or my own data set from Blender to use within this LDSO implementation. So this is the final goal. So I would like to move this live stream towards us being able to create a synthetic image sequence in Blender and then loading up this image sequence in the LDSO, then running the LDSO on this image sequence, getting the point cloud and the trajectory out of the LDSO, and then comparing like the performance of the estimation. Okay, so with this kind of plan of attack out of the way, let's start with the first task, that is fixing this bug. So you can see that running the dataset sequence 45 that is currently running here, it runs quite well. You can see that given that the algorithm is running really slow because it's the debug build and I'm doing like this video streaming simultaneously, you can still see that the results are quite okay, I would say. So the camera trajectory is somewhat resembling what is given from the images and the point cloud too. But what I will do now is I will quit that. I'm not sure if I can quit it this way. The pangolin thread has quit, at least. But maybe the loop closure thread is taking some time. It's not responsive anymore. So I will just kill that debug process. And you can see that I have prepared this launch JSON file with more lines for processing other datasets. And one of them is the dataset with sequence 02. So I will take that and comment this in and comment out the sequence 45. So this is everything. And now I will once again just take my IDE and press the debugger, the GNU debugger with this launch configuration. And we'll see if we get some kind of error. Okay, so now the debugger is attached to the process and it stopped at the main function. So we can simply continue that. And now we got an exception because this assert false is called here. So why is that? Let's take a look at the image sequence, maybe. Let me quickly find that here. Okay, so here you can see that this is the image sequence 02. And here we have our images, and here we have our camera.txt file, which contains the camera calibration. And compared to the sequence 45, here we are calling the crop, or we are defining that the images need to be cropped. Whereas here in this camera.txt, we want to apply a specific scale factor, or at least we want to apply a new camera matrix, which is given here with fx, fy, cx, and cy. So even though we are resizing the image sequence here from 12080 by 1024 to 640 times 480, we also want to define a new camera matrix for this scaled down version. And this somehow leads to problems with the code currently, because the code still wants to make an optimal K matrix, an optimal calibration matrix, which is called with the full keyword. So there's not like the crop keyword, but there's the full keyword. But it's actually not contained here, so it is not defined as full. So we could basically also write in line 3 where there is written crop, could also write full here. So this would then lead to not like cropping the image and calculating a new camera matrix, but just using like the full camera matrix that was supplied with this camera.txt file. So basically this one. The problem with this full is that we cannot use it because it is not implemented in the LDSO, which is up to this point quite weird from my view, because the full keyword was implemented in the DSO, I think. So in the direct sparse odometry, the predecessor of the LDSO, which, yeah, is a bit weird to me. But anyway, let's keep this camera text from the dataset. So this is the original camera.txt from the dataset that I downloaded from the TUM website. And you can see that with these new commands here, or with this new line, something is happening behind the scenes. And what actually is happening is given in line, I think 1011 or something. Let's quickly see. Yeah, like here. So you can see in line 20, no, not 20, but 1032. You can see that here we take line 3 that was extracted before. So somewhere above here. You can see that we get the different lines from the camera.txt file, line 1, line 2, line 3, and line 4. And here you can see also what is given in this specific line. So this line 3 could be crop, as we saw with this example from sequence 45 that can be used successfully. It could also contain the full keyword, as I just showed you. And it could also contain parameters, like basically the camera parameters, fx, fy, cx, and cy that I just mentioned. And there is something wrong with this line 3. So let's see. Line 1 and 2 are okay. So let's scroll down until we get to line 3 here. And in this case, we do not have, like in the case of image sequence number 02, we do not have the crop keyword, we do not have the full keyword, we do not have none, but we have those 5 output calibration parameters. So we can skip this part and this part and this part as well. And here we will see that in this case, we are getting the individual 5 parameters that can be given in this text file. So in this case, for sequence 02, we want to parse this line number 3. And specifically, we want to parse those 5 parameters here. And now there's one thing happening which should not be here. That is, in line 1036, we are still setting output calibration 0 equal to -2. And this means we are basically, if we take a look, somewhere here, if this is a -2, we are calling make optimal k full, which will then cause the exception because we are asserting the false expression. And this is just due to like a copy and paste error, I would say, that I made before. So in the original code base, this line is not there. So what we need to do is we need to delete that, save the undistort.cc file, stop the debugger, and rerun the debugger. I mean, before we rerun it, of course we need to recompile. So let's build that. I hope the stream will not crash. Get a bit louder. I hope this will finish in a minute. Shouldn't take too long. Okay, if this is taking much longer than I expected, let's take the time to discuss what we will do after this compilation is finished. So what the LDSO will create once it is finished with the whole sequence is that it will generate files, which you can see here in the project. So one file it will create this file, unfortunately, in the .vs code directory. It will create this point cloud ply file. And it will also create two text files. Let me quickly check if I can find them. Yes, the results.txt file and the results.txt.noloop file. And we will take those files, the point cloud and the trajectory, and visualize that in Blender. This is what we will do at the end of this stream. Okay, so the compilation is finished now. It's 100% compiled and it's linked as well, so we can start it now. So let's go back to the debug viewport layout or view, and now we can just press the play button, and hopefully this will work, but it's not working. Let's quickly check. Something's wrong. Let me retry. Sometimes it works to just try again. Okay, now magically it's working. I don't know what was the problem, but yeah, now it's in the main function, and now we can just play the sequence. Maybe before we do that, let us scroll down to the important part, which is in this thread, the processing of the individual images. That is, here we get the image from the reader using the function call of getImage. And then we can use this image to do something very important, and that is to add the active frame with the image data and the current image index to the full system. So here I want to set a breakpoint because this line of code will be called several times with a changing index I. So let's continue with the debugger until this is happening. Okay, so now we can see that it looks like the dataset was successfully read. Here you can see, by the way, the output calibration that was given in this text file. So if we compare that, we get 0.4, 0.53 and 0.52 times. And we get an output resolution of 640 by 480. So this is ideally working by using the past arguments and therefore the camera calibration that was given in this camera.txt file. And it will find, so the LDSO will find a rectified camera matrix, which is our calibration matrix, which looks like this. So it's a 3x3 matrix with fx, fy, and cx and cy given here, even though the input resolution was differently. Okay, so this breakpoint will cause the debugger to stop here several times. But what I want to do is I want to add this I variable to what is called the watcher. What did I do now? Somehow misclicked. We can use this add to watch. And now we are watching this variable I, this index, to see what kind of values this takes. It's not very useful in this case because the I variable is here displayed as well. But if we continue with running the main thread, we'll see that now the window is opened. So this is the user interface. Here we have different settings with sliders and labels and so on and so forth. And currently we are at image with ID 1. So if we continue that, you'll see that even though the first time was very quick, the second time now is a bit longer. So something is happening, something different is happening when we put in the first image, and another thing is happening if we put in the second image. So there is a distinction here somewhere in the code. But we can continue to run that, and you will see that it still takes quite some time to process one frame. It takes about, I would say, like maybe now almost 10 seconds, which is quite long. But we can maybe keep both windows open. And you are also you can also see that the user interface is not refreshing. So even though I'm resizing the window, you can see that we have those black bars here. This is because we need to have this the render loop for drawing this window, and if the debugger is stopping our execution, this the redrawing is not happening as well. Now that I have clicked on the play button, one iteration with the main thread and the user interface thread is done, and therefore we have this newly drawn window here. Okay, now we are at index equals 4. So let's continue. And I think somewhere about index 7 or 8, we should start to see the first camera pose and the first point cloud. So this is index number 5. This is index number 6. So currently you can see that the render loop is running, so everything is resized. But now that we are stopping by using the debugger, you will see that now the render loop is not executed anymore, or it's stopped basically. So let's continue with index number 7. So currently image number 7 is processed. I think it's actually image number 8 it should be. Because the index should start with 0, I think. Okay, but here we are at index equals 8. And now with index number 9, I think we should finally see something. Okay, index number 9, let's process this and let's see. Still nothing is happening with index number 10, let's see. Okay, now we can see that with index number 11, so after processing index number 10, there was enough information to get a point cloud, which I cannot navigate the viewport because the debugger is now stopping the execution. We can see that this point cloud is generated and there is this camera object created here. But behind the scenes, there's not only like one camera object, but there is a whole at least 10 camera poses, which are not displayed unfortunately, but they have been used to initialize the LDSO algorithm. So we could take a look, if I'm not mistaken, we could take a look at the full system. Let's see if we can find it here. So here's the full system. You can get the instance. And you can see that it has several state variables, like, for example, is lost, init failed, initialized, and initialized is currently set to true. So this means at this point, the LDSO is initialized. Now there is the possibility to press this reset button here. And this will, as the name suggests, it will reset the LDSO to the initial state, which means that it will still, not be initialized anymore, but it will take the image sequences from index number 11. Let me check if we are at index number 11, yes. So the image sequence from index number 11 will be taken, and from this a new initialization is being calculated. So this is something we need to take into account, because when we operate if we run the LDSO in real time, like with a real camera, it might happen that the LDSO will start in a configuration that is not ideal. Maybe we are moving the camera at this point, like readjusting the camera view or something, and this would then mean that all the estimations from the LDSO are not useful for us in this situation, so we need to restart or reset the LDSO. So to do that, I will continue the debugger here, and I will now, if I manage to do that, click on the reset button like this, So now we are at index 13. Let's take a look at the full system. And you can see that now the full system is not initialized anymore because I have pressed on the reset button. So now it will start, once again, it will start over to take the image sequence and try to estimate the camera trajectory again, to basically initialize the system. Okay, so now you saw that the first call of this add active frame was a bit faster than this current call, which again leads us to the it will tell us that the LDSO will handle the first image somewhat differently than all the subsequent images. Okay, so now I can play the game again with pressing the play button, or I can just deactivate this breakpoint for now, so that we at least will see a trajectory again. This should be now faster a little bit. Okay, I just want to have the LDSO running in a state that we can see the estimated trajectory and the point cloud as well. You can see that now the user interface is responsive. Again, I can zoom in, move my view, and rotate. This functionality is provided by the Pangolin library, which is a library that will create this window for us, and it will also allow us to add those checkboxes here to display an image or a video, and of course also draw this 3D geometry in this 3D viewer. One thing that would be very nice to have, besides many others, is that now that I'm just waiting, I have no idea at what kind of image the LDSO is currently working on. So it would be nice to have here another label, I would say, at the bottom, which displays the current index of the camera sequence or the image sequence that is currently being processed. So this way I'm a little bit more prepared to know when the LDSO is initialized. Okay, so now probably a lot of images have been processed. Let's quickly reintroduce this breakpoint here and see what kind of index there is. So here we have index 39. So it seems that it took a little bit more, or at least more images than before to initialize this time. But so far everything looks okay, I would say. Point cloud looks correct to me. The camera movement I cannot really judge because it's really laggy at the moment. But this seems to be okay. Alright, so now let's try to change something here. What I would like to change as a first step is to draw the 3D coordinate system and also the individual coordinate systems of the cameras. So let's see how we can do that. So let's go back to the code. And let's see. So where is the drawing happening? We have this full system, and the full system will contain everything that is somehow related to the operation of the LDSO. The full system will also have a viewer associated. And I think the viewer is here. Here the viewer is set to this viewer instance that is of type Pangolin DSO viewer. So this is the class we need to take a look at. So let's go into that, and the associated header file is the DSO viewer.h. So let's take a look and let's maybe go through what is happening here. So in this LDSO namespace, we have a point cloud struct. So we have this struct called input point sparse, which has a u and a v coordinate. These are floats. So I would say that these are the pixel coordinates in the image. Let's maybe call that horizontal pixel coordinate. And this should be the vertical one. Now, the interesting thing is what range the u and v variable could be in. So they could be in range 0 to 1. They could be in the range from -1 to +1, and they could be in the range of pixel coordinates. So I'm not sure if this is the pixel coordinate system here, as I just wrote here, or if this is, for example, the normalized device coordinates, the NDC. We'll need to check that later, I would say. Then the eye depth. Oh, there's a typo here. Eye depth. This is probably eye depth. This is interesting to know that there is a typo, which is the inverse depth. And the big question is, in what kind of coordinate system is this? And this will probably be in meters, but the problem with meters is that we do not have a reference. We are using a monocular image sequence, which means that we cannot find out the real measurements, the real distance to objects. So this will be probably in, I would say, like in quotation marks, meters, but falsely scaled. It will have an ambiguous scale, like an unknown scale factor. Then we have a Hessian, which I don't know what this is, to be honest, and we have a relative observed baseline, which will probably also be in meters. So the baseline is, if we have two cameras, the baseline is the line connecting those, so basically the translation vector between those. And this will also be in, let's say, meters. Then we have the number of good residuals. Count of whatever good means, residuals. Then we have the color. The color, which is an unsigned char. Okay, so we have the unsigned char, which means that we only have one grayscale value. So this will be in grayscale. And this will be between or in the range of 0 to 255, which is 2 to the 8. Oh, okay, let's keep it like that. Bits we can use, or 1 byte. And then we have something called the status, which can be very interesting for us to visualize the point cloud in a specific way. Yeah, I don't know what the status is. I need to find that out. And maybe we could take a look at the function call that will create the point cloud. So here in the end, we have the viewer, and we can call save as polygon file, so PLY file. And this will create this, it will create the file on the hard disk that will contain this point cloud. So if we quickly take a look into that, we can see that it takes a file name from us. It will open this output file stream. It will lock the 3D model. That will then it will iterate over all the keyframes that we have. So the point cloud, this is important, will only be built based on the keyframes, so not the individual frames, but the keyframes. And we are summing up the total number of points by getting each keyframe from our list and getting the number of points for each keyframe and adding that to this total count of the points. This will be important when the PLY file is written, because in the beginning we have a header, which is this part. And in this header we need to give several information about the point cloud or the data structure. And one of the important data that we need to give here is the total number of elements. In this case, we only have vertices, so we are only storing vertices in this PLY file. We could also store polygons, which consists of edges, and edges once again consists of vertices. But here we do not have a mesh, but we have a point cloud, and therefore we give it with this command. We say, okay, we have those vertices defined in this file, and this is how the header is being created. So let's compare that with the file that was created already. Maybe let me go back to the LDSO switch here. And here I have created this folder backup results. I did that because in hindsight, I knew that we will run the LDSO multiple times on different image sequences, and I just wanted to store the data that we can later use to visualize that, and there will not be anything broken or something. So here we have this point cloud and we have the results, which we will talk later about. And let's open this PLY file. And this file is quite large. It has 16 megabytes in size. And you can see that here the structure of this PLY file is given with this PLY keyword. Then we have the format. This is a human readable file, so we could also write out a binary file, but in this case it's human readable. It's the text format. We have in total about 630,000 vertices, and each vertex is given by a property, namely by 3 properties, that is x, y, and z. So these are the coordinates. We could as well write out the r, g, and b values to color the point cloud. So this is probably something I would also like to do here. But I do not want to break the file format here with my own creations at the moment. So let's keep it like that. So we are still in the analysis phase. So we have this implementation running now. It seems to be running correctly. And now we are looking into the details of how the algorithm is really working behind the scenes. And this is one important part, because at some point we naturally want to compare the point cloud with maybe a ground truth or something, a reference that we have, or post-process this point cloud to maybe generate a mesh. So there are many ways we could we could explore here, but for now let's just keep things simple with analyzing what we have. Okay, so now after this header is being written, there is a list of all the individual point coordinates. So x, y, z, x, y, z, x, y, z, and so on and so forth. And this is the whole file. So the PLY file format is really a very nice file format because it's so simple. There's also another file format which we could use, which is the OBJ, the object file format, wavefront OBJ, sometimes it's also called like that, where we could also store our data. But the creators of DSO and LDSO, they decided to use the PLY file format, which is perfectly fine. It is a very nice and easy to handle file format. And we can see that this file format is written in this save as PLY file function. So here we have the header. And what is done next is we are writing the keyframes, which is weird. So we have already iterated over all the keyframes, but we do that again here. So let's maybe add a comment. Maybe let's add write header, write point cloud data x, y, and z. And this is implemented in the keyframe data structure. So we have the keyframes, which is a standard vector of shared pointers to a keyframe display. So those keyframes are not actually the keyframes that we have defined, for example, in this frame.cc file or the frame header file, but those are like separate. This is a separate data structure. So let's take a look into that, into this keyframe display. So this is defined in the DSO viewer.h as well. So just as we had this input point sparse, here we also have this class keyframe display. And the keyframe display does not have a standard constructor, it seems. It does not have a constructor at all, but it only has methods to set the keyframe display from a keyframe or from a frame. Okay, I'm a bit confused about this description here, because this is, okay, this might be a keyframe, okay, but actually this is a frame hashing, as you can see here. And here we have the points from, this is actually taking the points from a frame, it seems. Okay, I'm not sure what this keeping some additional information is. Maybe it's related to this camera calibration that is passed here. Okay, but we have this keyframe display. Or I think we have many of those keyframe displays in our scene, depending on how many keyframes we have actually. And let me think. So we can draw a camera, it seems, and we can draw a point cloud. Then we have this less than operator, which allows us to compare IDs of the current keyframe display and another keyframe display, which is passed here. Okay, and here we have this numPoints method, which we saw. So this is just taking, it will just take this number of sparse points, which is probably a member variable like here. Okay, so num sparse points is used to iterate over every point. And then it is comparing in the original input sparse point cloud. So this is of type input point sparse that we have looked at before. For every point in this point cloud, I would say, we check if the inverse depth, with this typo, is greater than 0. So we are checking, is the point that we are looking at, is this actually in front of our camera? And if this is the case, then we increase the count. And this is how we can calculate the number of points. Okay, I think this is understandable. And then we have the save method that we are currently trying to gain insight into. So let's take a look at the implementation of that. So in the DSO viewer.cc file, we now have the save method of the keyframe display. And if this is called, then a few things are happening. First, we get our sim3 transformation. So sim3 is a transformation that contains not only translation and rotation. This would be an SE3, a special Euclidean Lie group. The sim3 Lie group, this will contain scale as well. So translation, rotation, and a scale factor. So this is created here as a placeholder. And next we want to check for the origin frame. Which is a shared pointer to a frame. Okay, so here we check if origin frame is a null pointer. Let's check if this is the null pointer initially. So we have the keyframe display, yes. And then we have, what was it called? Let me quickly check. Origin frame. Origin frame and keyframe display. Keyframe display. Ah, here. Okay, so here is the origin frame. And this is initialized in the beginning as the null pointer. Okay, so somewhere we are setting this origin frame. Let's see if we can see it here, if origin frame. So this is at least used twice. Okay, here's a third time. And here it is set. So set from the frame. It is setting this as fs. Cam to world. Okay, I suppose this get pose opti is giving the world to camera transformation. Which would make sense. And by getting the inverse of that, we get the cam to world transformation. And we also can get the scale. And in this case, we set the origin frame as the, okay, yeah, okay, this makes sense because fs, what is fs? Is the frame. So the fs is that transformation from world to camera. And if we create a keyframe display from this frame object here, then this frame object is the original pose, like the original world to camera pose. So we set that here. And probably the same is happening with the set from keyframe. So here we have the frame Hessian. We extract the frame from that. Okay, this is not happening here. That's interesting. So set from keyframe will not update the origin frame attribute. Ah, okay, it's the origin frame. It's not the origin keyframe or something. So this is only related to the frame. Okay, it's still a bit mysterious. But I feel that I know enough now to work with that. Okay, let's quickly check again. So we have to save. Okay. So here we are basically asking for the frame associated frame, and this is, in my view, the world to camera transformation. World to camera transformation. And this is set by set from F or something method. Okay, so here set from KF is also calling set from F if it does have a frame. This is still quite complicated in my view. But this means that we are just taking the frame the associated frame and we are assigning it. So the point here is that we do not want to distinguish between frame or keyframe, but we want to simply know, does this current frame, whatever it is, like is it a frame or a keyframe, doesn't matter. It just matters, does this frame contribute any 3D points to us? In my view, these can mainly only be keyframes, but maybe here it does not matter if this is a keyframe or a frame for visualization purposes. Okay, so this is not wrong what is written here. Maybe it's not very precise, but this is definitely true. So in the set from frame method, we can set this origin frame. And it should also be true that this is the world to camera transformation. Because here we are taking the camera to world transformation, assigning it to SWC, which could mean that this is the world to camera transformation, but we actually need to read it from in reverse, basically from camera to world. So cam to world. And this one is world to camera, and then the inverse is world as cam to world. I'm getting confused myself here. But okay, what we in essence want to find out is what is the relative transformation. Oh, thanks for following. X3B00D502. thanks for your follow, and welcome to the stream. Yo, nice. How are you? Welcome to the stream. And I'm always interested in how did you find me? So how did you come across this stream, and what are you interested in? Maybe you can tell you that. You sound Polish or Finnish. I don't know. Yeah, maybe. Maybe you're right. Maybe I'm Polish, maybe I'm Finnish, maybe I'm German, maybe I'm all of that. So yeah, you're probably right. From software and game dev category. Ah, okay, that's nice. I'm always not sure like what do I need to do to appear there, but if it's working, then this is good news, at least. Yeah, maybe to inform you what I'm doing here. So I'm looking at the LDSO, the direct sparse odometry with loop closure. Do you know what that is? I use low to high views. Ah, interesting. Ah, that's a nice method. Why are you using low to high views? What makes low view streams more interesting than high views? I use C# in Unity. Okay, yeah. So you're a game developer, it seems. I don't know, lots of other nerd stuff. Yeah, okay. Yeah, this is a nerdy topic. Yeah, I'm actually not using Unity here in this stream, at least not yet. I'm using an implementation of a render engine, which is based on the Pangolin library. So no physics library, no sounds, and so on and so forth. I model a 3D model too. Okay, that's nice. Oh, itch.io. Let me check if I can do that off stream. Ah, so you have cars. You are modeling cars. I mean, I can show that here. Oops. Where are you modeling that? In Blender, it seems. Okay. Yeah, nice. Cool. I have actually added the Blender search tag today to this stream because I'm planning on later loading up this PLY file that we have here, this point cloud PLY, in Blender and visualize the camera trajectory, which is stored here in this results.txt, and like code up this import script in Python to visualize the data in Blender. So this is what I'm planning to do later, but currently I'm still in the analysis phase of this code here. It's medieval basic style of 3D modeling. Okay. So what kind of game will it be, or is it just a modeling practice, or is it related to a Unity project? That's cool to have fellow 3D guys here. Shitty mechanic. Ah, okay, this is your game? Is an Arabic game made by one developer. The game main goal is to build cars and bikes. Ah, yeah, that's cool. So there's quite a lot of physics involved, I would say. Okay. Yeah. Nice. Okay, good luck with that project. I will take a look at that later. Unity and Blender, that's the great combination. I would say that this is quite common. This was my biggest project and it's kind of lame. Oh. Why lame? It looks quite good. Why do you think it's lame? I like it. Well, I did not see the video, so maybe the car physics is what you call lame. I don't know, but yeah, I will definitely take a look. What do you make? Yeah, how to describe? Do you know what a Visual Slam is? Do I have this still open? Oh no, I cannot show you, unfortunately. You don't know? Okay, but I have this in my GitHub repository. Let me quickly pull that up. So let's see. So here's a short demonstration with this animation here. Unfortunately, it's quite small. But the idea is you have an image sequence, so basically a video which you can see here, and this video is being analyzed, and you reconstruct the camera movement, the camera motion from that, and the 3D point cloud. So this is a Visual Slam, which is short for Visual Simultaneous Localization and Mapping. And of course, you can take that stuff and import this into Blender. And yeah, you can ideally avoid having to model of all the stuff, but you are just taking a camera and digitizing your real environment. And yeah, it's I agree. It's complex AF, and that's why I'm doing this stream. So I'm just trying to learn it. So this is the background. And of course, at some point I want to move from this complex stuff into Blender and try to use this the data that is generated here to create virtual worlds or whatever. Yeah, that's in a nutshell like the idea. And currently I'm trying to see how the point cloud is generated. So when you are using Blender, you probably know the PLY file format. So this one here. And this file format is generated in this Visual Slam implementation. And the thing is, where does the data come from? This is the big question. Nerd stuff is very interesting, but how do you focus on a project? Let me check. Okay. Unfortunately, the text was cut off. How do you focus on a project without getting sidetracked? Yeah, good question. How do you focus on a project? Well, yeah, I don't know. That's also my problem. I think what is very important is to have a goal in mind. With a clear goal, you can stay focused. And do not try to solve every problem at once. Like, try to make that goal that you have, the ultimate goal, try to create sub-goals, like smaller goals that you can achieve. And ideally those goals should be manageable in maybe like a day or something. And this way you, like, the good thing in my view would be that you can say you have accomplished a goal and you have this good feeling. And then once you have accomplished this goal, you can then continue and you stay motivated. But yes, yeah, my brain goes anime always, yeah. Oh, I missed this other. Would you rather spend 10 hours looking at screen and smashing keyboard or watch anime? Well, smashing the keyboard? I don't know, it sounds like fun, right? No, yeah. It's a very difficult topic in my view. You have to find something that motivates you with your project. And my motivation is to gain the knowledge how this stuff works. This is my motivation, and for this I'm willing to skip like anime or other procrastination stuff. I don't know. I'm not a big like I cannot give you like the important tip or something, but maybe this helps you. I hope. Okay, I will continue now with the analysis of the point cloud. So we have those points that are written in this PLY file, and this is actually happening with the, let me check, with the save method. Okay, so in the save method we are first extracting the camera to world transformation given our frames, like the keyframe or the frame that we have, and we need that to transform our points from camera space to world space. So we want to basically back project our points that we have found in those images, like the 2D feature points, want to back project them into the 3D world to create this 3D point cloud. And what we need to do this is written here. So first we need to extract the depth, and this is done by taking the inverse depth and inverting it. So 1 over the inverse depth will get the depth for us. Before we do that, we need to check if the inverse depth is smaller or equal to 0. That is, the point is behind the camera or at the current position of the camera. In this case, we want to skip those points, so therefore we have this continue. And once we have the depth, we can calculate the x, y, and z coordinates in world space. That is, we take our u and v coordinates. Those are our pixel coordinates. So where in the image is this current point located? Then we multiply that with the focal length in x, basically in the inverted focal length. That's why the I is here. And we add the principal point in x and y. This way we convert from the image space to camera space. So this part is converting from image space to camera space. And when we multiply this depth value to that, we are still in camera space, but we are now extending our ray given our depth data. So you can see that, you can imagine that maybe if we pull up Blender here. So we can have the points of our point cloud, for example, if my Blender is reacting, yeah. So we have those points here in world space, for example. We could also look at those points in camera space. That is, I now switch to camera space, like whoosh. Now I'm in camera space, and those points are now related to the camera coordinate system. And every point that I can see in my image here has an associated depth, and I'm now just simply back projecting those 2D locations in my image back to the 3D locations so that I can describe this point in relation to my camera. So like this ray, for example, here. So my here, and then the next ray that tells me where this point is, all related to camera space. So this is in a nutshell what is happening here in my view. Of course, maybe this is wrong, but that's my understanding of this. Let me quickly get rid of these annotations. And now the problem is that this camera could be somehow translated in the world as it is here, but to make it maybe more clear is this whole setup could be moved somewhere here. So we need to find out this transformation from world to camera or vice versa, to find out not how the individual points are related to my camera, but actually to find out how they are related to my world coordinate system. So this is what, in a nutshell, in my view, is happening here. So we are taking our pixel coordinates, u and v. We are converting those pixel coordinates into camera space. So let's comment this in here. Image to camera space conversion. For the z variable, or for for the z axis, it is quite easy because this is basically the depth. So if we take a look again in Blender, and if I show my coordinate system of the camera, this one would be the world coordinate system, but I want to show the camera coordinate system, the local coordinate system, which is this one. You can see that for the x and y axis, we need to somehow take into account what my camera calibration is. So I need to take in my focal length and my principal point to know in what kind of direction the rays are projected. So they should be like somehow projecting here, given my field of view. So this is my field of view of the camera. And so this is like the x-axis and the y-axis. The horizontal and the vertical axis, they are quite complicated to calculate, but the z-axis is very easy because it's simply like the distance from the origin of the camera to my 3D point, and this is simply the depth. Okay, and here we are taking the camera, the coordinates, the x, y, z coordinates in camera space, and converting it to world space. Conversion. Let's maybe write out this number 2 here. Okay, and once we have this 3D vector that is given in world space, that's the point in world space, PW, then we can simply write this out with this line to be included in this PLY file, and every coordinate is separated by a space. And this is already all the magic that goes into creating this PLY file. Of course, the big question is, how do we compute this inverse depth? And how do we find the u and v coordinates from the image sequence? So if we are processing each image, we first need to find those features in the images and then use those features to calculate an associated inverse depth, or ID path, as it is written here. Okay, so now we have looked at how the point clouds are generated. Now what we could do here at this point is we could add additional data here. For example, we could add the color. I'm really not sure if I want to do that, because if I make a mistake here, things will not work. And actually, I also want to do something differently. That is, I want to change the 3D display, and I do not want to change the export, because the export is fine in my view. So let's stay with the other task that I introduced in the beginning of this video, because we of course want to finish that. But anyway, we have the viewer here. So in this viewer.h file, we have the input points parsed that we have discussed, and we have this keyframe display that we have not fully discussed, but in general we know what is happening here. Okay, and here we have a drawCam method. Let's take a look into that. So what is happening here? Again, we are extracting the camera to world transformation by getting this pose, which is in world to camera configuration, and then taking the inverse from that to get the camera to world transformation. And we can do either this to get to use the normal pose, or we can get the pose after optimization. In any way, we need to have the camera to world transformation. Because the camera to world transformation is the one that is actually being used to draw the camera pose, I believe. Let's see if something else is here. No? Okay. Okay, so this is the important thing to have to draw a camera object. To draw a camera object in the 3D viewport. We have the size factor that is passed here, which is, I think, a constant. Let me see where this is called. This is probably called... Ah yeah, in the DSO viewer. Okay, so in this viewer we have this run method, which is running indefinitely. So this is I think this is an endless loop. Let's see if this is somewhere here. Yes, okay. So this run method is called once, and this will not return. So this is running forever until we are stopping the Visual SLAM system. So you can see in this run method there is really like the important stuff happening that is related to the 3D display of our scene. So first we are using Pangolin to create a window and bind that window to our current, I believe, to the current what is the context called? Like the graphics context. We are basically creating a window and assigning the inner part of this window to our draw calls that we will see later. And this is called main, which we could change at this point. Let's change this to LDSO Twitch. Okay, then we are logging some info and we are setting a UI width. Okay, then we are creating a visualization camera with this projection matrix. So this is related to the camera that we are using to look around in our scene. And here you can see how it is created. So we have this width and height of the projection matrix. So this is basically, this should be the same as our window size. And then we have the focal length in U and V coordinates, so in horizontal and vertical. This is, you could say that this is our field of view of the camera. So how should this camera be a wide angle lens or should it be a telephoto lens? There is probably a different way to define that. Let me check. Pangolin projection matrix. Okay, there's only one method to do that. Okay, that's interesting. Sometimes there's also the possibility to define a projection matrix using, for example, field of view and near plane, near clipping plane and far clipping plane and so on and so forth. But this is also included here. So you can see after this focal length, there is also the principal point to be defined. And then there's a Z near and a Z far, which is the clipping plane. Maybe to explain that. If we have a camera like this one, then this camera can have an area, a region that is visible, that is not clipped. And we can visualize that in Blender by going into the camera details and then going into viewport display and then showing the limits like this. And this will draw a line with two yellow dots, where one yellow dot is depicting the near plane and one dot is depicting the far plane. So if I now take my clip start and clip end, which is in Pangolin the Z near and Z far setting, if I adjust that, you can see that now I'm changing my range of the camera. And if I look into my camera view now, you can see that depending on how I define this near clipping plane, you can see how, at what distance I want to draw my objects. And same with the far plane. And those are like general computer graphics ideas that you will find in every 3D software possibly. Okay, next we have a model view look at. So a model view matrix is defining how my camera is oriented and positioned in 3D space. So this one takes in an X, Y, and Z location, and then an L, X, Y, and Z. Which I do not know what L means. Looking at. Okay, look at. Alright. So this can also be easily explained, and we have this a negative y-axis as the up vector. So let's take a look in Blender again. If I create a new camera object here and place it here, and I create also an empty object, which should be my target, I can now assign this camera to follow or to look at this this target. That is called in Blender a track to constraint. And this way you can see that if I apply that, when I move this target, my camera is now following this this look at target. And what is happening behind the scenes is a new model view transformation matrix is calculated, and this can be done in Pangolin with this line of code. with this command. And here you define where should your camera be positioned in world space in X, Y, and Z. Where should it look at? And what axis should be the up axis. So if I, for example, take this camera constraint and I change the up axis to be not Y, but for example X or Z, you will see that this will have different implications. So Z is not working because we are using -Z as the track axis and up axis also as Z. But with X, for example, this would then have the behavior that the camera is somehow flipped sideways. Let's move into this camera. Now we can see that the camera is moving like this. As opposed to the y-axis, this should be the correct way. Okay, so with this out of the way, we now know how the basic scene is set up in Pangolin, and now we have some other parts. For example, we can have a view. I think this is probably the sidebar. No, this is not the sidebar. Ah, this is the 3D display. Okay. So here we have a view or an area which is responsible for the 3D display. And in order to create this view, we need to create a handler or set a handler to a 3D visualization camera that we have just introduced above. So this is the camera which we are taking to, or which we are using to view around, or to inspect our scene. But I do not know what those bounds are. Okay, so this is bottom, top, left, and right. Bottom is 0, top is 1. Left is the UI width. Ah, okay, now I see. Okay. Okay, so this is definitely, as it's clear, this is the 3D display. But this is done in such a way that we have enough space from the left-hand side, because this third argument is the left distance, enough space to fit the user interface there. So if we take a look here, we have this user interface on the left-hand side, and this is just like the beginning. So the width of this left settings bar is the beginning of our 3D view here. Therefore, the left coordinate is set as the UI width, which is a constant in this code. Then we have another display for the video, where just the aspect is being set, given the width divided by the height. Then for the video, we also need to create a texture object. So we need to allocate, on the graphics card, we need to allocate space to fit our image from the video camera. And this has, of course, the width and the height that we already know. And then let's see what else is here. Why do I not see the constructor? Okay, so there are multiple overloaded constructors. For example, a simple standard constructor. We have a constructor that takes in another GL texture, a reference to that. And another one, and then we have almost the one that we are using here. So this one takes in a pangolin typed image, and if we want to sample the image linearly, so using bilinear interpolation, I would say, when we scale the image. And then we have this constructor which takes in the width and the height. We have that here. Then we have the internal format, which in our case is an RGB image, even though we are only having grayscale images in our case. Then we are not sampling using bilinear interpolation. This is set to false, which probably means we are using nearest neighbor sampling. Then we have the border is equal to 0. And we have the GL format, GL RGB, and the data type, unsigned byte. Okay, so that means, to me, this seems that we are expecting our image data to consist of 3 channels, actually, where each channel can contain pixel intensities which are stored as unsigned chars or unsigned bytes. So that means they should have values in between 0 to 255. This is something that we need to take into account because we want to have the correct format for display. And this is everything that is needed here. Then we are creating another display, just as with the 3D visualization. Once again, we are using this distance for the UI width from the left-hand side. We are setting some kind of layout, and we are adding this display for the video image that we just created. Okay, so let's maybe move this here to the display, because here we want to set up the video display. Okay, so we can create individual displays, and in each display we can place another display, it seems. And the bounds are given relative. Okay. So next we are creating a panel which is called UI with the bounds of bottom, top. Bottom is 0, top is 1, and left is 0, and right is this time the UI width. So we are now creating this panel on the left hand side, which should have the final width of this UI width. Okay, and then we are creating variables for Pangolin. integers, booleans, and doubles. And I think this is the part where I want to introduce another name or another display, because those are local variables anyway. So let us try to do that. I now want to try to introduce the frame number, the frame ID. And this will be an integer. This will be called settings frame ID. I hope this is not taken. Okay, doesn't seem like it. Okay, now let's see what the argument list is, because I do not know Pangolin, to be honest, so I need to look that up. So we have a name or a var value generic. Then we have a constant int reference to a value, toggle, flags, double min, double max. Okay, I think this way should be fine, but I do not have a maximum value of the frames. I mean, I could get that from the data set. But maybe 0 means infinity. We check the track FPS. This is given as 0, 0, 0. And it still is displaying values greater than 0. Or is it? Okay, so this one is only displaying 0 all the time, it seems. The keyframe display. Let's take a look at the one above, but this is the same. So I'm not sure, but it seems that 0, 0 here means infinity. And then we had this flags, which is also 0, and if it's toggleable, which is false, which should be fine. Okay, and this is not given yet, or taken. Okay, let's see how the data is refreshed. Here, update parameters. Okay, where's the FPS? So we can just assign the track FPS a new number, it seems. Okay, so let's see. mutex lock. We need to maybe pay attention about locking the mutex. Where's the other FPS? Map FPS. Is this not even set? This would explain things. Okay, it seems that this is not even set. Okay, let's see. Let's finish this one first. Do we have somewhere an information about the current index? Last end tracking ems. Not sure where I should put that. Need refresh all. Refresh all. Okay, let's do it here. Update the current image index. Okay, so I do not know if we need to lock and unlock a mutex. We definitely need to know the ID. Where do we get the ID from? Oops, I'm sorry. Do we have the current ID in the viewer already? We have this all frame poses, which could be information for us. We have a current cam, which is also interesting. Active keyframe IDs. So those are many ways to go. Okay, so I'm not sure if there's one specific ID here, but let's try to work with that. So we have all keyframes, we have the current cam, and it's maybe not interesting, active keyframe IDs. So those three data structures are the ones that sound interesting to me. So let's see if we can take the current cam dot, maybe get ID. Hopefully this is what I need. And hopefully this is even being set. So let's comment out the other things. Usable data structures. Okay. Let's get rid of the other statements. So ideally, this would already enable us to see the current frame ID in the user interface. Of course, I want to rename that. So the syntax is we have this UI, which is this name, and then we have substrings basically. So this is a frame ID in my view. Okay, let's maybe try that out to check if I have messed something up, which I hopefully did not. So let's rebuild the code.